Oxalic acid. And we'll learn about all these acids here in biochemistry. We start in chapter 17, I think. All these acids are going to come into play. They're biologically important. And they're the IUPAC name we call them is ethane dioic acid with 2 carbons and a carboxylic acid on each end. Propane dioic acid, 3 carbons and a carboxylic acid on both ends, which is malonic acid. Succinic acid is butane dioic acid with 4 carbons. Glutaric acid is pentadioic, 5 carbons. And adipic acid is hexadionic, which is 6 carbons, and then 2 carboxylic acids on the ends. Okay. Garbage bags from potato peels. Garbage bags are a major problem with our environment right now. They do not dissolve. They're not biodegradable. One problem states the North accumulation of trash. We try to control the amounts of garbage they produce. Many institutions in the town practice recycling aluminum, paper, and plastics to help control the amount of garbage we produce. The I can't talk today. The plastic trash bag is a big problem. Okay, we stuff the trash bags full of biodegradable garbage and we bury it in a landfill. But soil it can't break down the plastic to get to the biodegradable material inside. So it doesn't really work very well that way. Researchers producing bacterial metabolism are providing new materials. They're the properties of plastic, but are easily biodegradable. Okay. Sheets of plastic can be made by polymers of lactic acid. Maybe talk about lactic acid. Builds up in the muscles during anaerobic respiration. When the muscles are pushed to maximum, where they work out without oxygen, one of the byproducts is lactic acid. Okay. We know what polymers are. Polymers, when we dehydrate materials, we lose an H and an OH and we link things together. We can link these monomers together and make a polymer chain. Okay. So lactic acid is a natural carboxylic acid produced by the fermentation of sugars in milk and in working muscle. Okay. Many common soil bacteria can break down polylactic acid. Okay. Trash bags made from this polymer would be quickly broken down in landfill soils. So making plastic from lactic acid requires a huge supply of the carboxylic acid, lactic acid. Okay. We can produce an enormous quantity of lactic acid from garbage. When French fries are produced, nearly half of the potato is wasted. Those who work in fast food restaurants know that. That amounts to 10 million pounds of potato waste each year. Okay. When cheese is made, the curds are separated from the whey, and several billion gallons of whey are poured down the drain every year. So potato waste and whey can easily be broken down to produce glucose, which in turn can be converted to lactic acid to make biodegradable plastics. So we use our trash to make biodegradable trash bags. PLA plastics have been available since the early 1990s and have been used successfully for sutures, resolvable sutures, medical implants, and drug delivery systems. Okay. And this is your polylactic acid, PLA. And this is lactic acid that's linked together. This is lactic acid, 3 carbons. So here's your 3 carbons. Okay, here's your oxygen group at one end, oxygen group at the other end, and your carbonyl group. Okay, and it links by a dehydration reaction. We take H from one, OH from another, and we make this link right here. Okay, so it's a dehydration reaction, and we just link lactic acid monomers together to form the polymer, which is polyacetic acid. Okay, and that's what makes sense we use for plastics now. Okay, nature's also provided biodegradable plastics that are produced by bacteria. Most common of these is polyhydroxybutyrate, PHB, made by Bacterium allergenis eutrophus. PHB is a homopolymer made of a single monomer, okay? 3-hydroxybutanoic acid. So there's 3-hydroxybutanoic acid. We all know that terminology now. Okay? And we link that together. Again, dehydration reaction. We take an H off of one, OH off the other. We form water, and it links these two together, and we lose a water molecule in the process. Okay? That's how you make polymers. And it's a homopolymer because there's only one type of acid, one type of compound involved. This natural polymer does not have physical properties that would allow it to be commercially successful plastic. Okay? This leads to interest in making heteropolymers, polymers composed of 2 or more different monomers. One such polymer with useful properties is heteropolymer of beta hydroxybutyric acid and beta hydroxyvaleric acid, which is given the name was called bipole. Okay, and this is bipole, and it's the linking of two different monomers. Again, you're linking the OH and the H. So we kick off water to form this bond right here. Okay. You get rid of the H and the OH and bond it right to the carbon. Okay. So it's a dehydration reaction we talked about to make bipole from these two different types of carboxylic acids. Okay. Bipole does have properties to make it commercially useful, and it's completely broken down into carbon dioxide and water by microorganisms in the soil. So it's completely biodegradable. Right? Because bacteria produce a low yield of bipole, scientists produce transgenic back plants in hopes that they will produce a higher yield of polymers. So we can modify the plants to produce more of this polymer that we need. We also have problems with this approach. Okay. For the time being, biodegradable plastics cannot outcompete their non-biodegradable counterparts. What does that mean? It means there's more money in making plastics that are not biodegradable than are biodegradable. That's just the way it is in the world. Okay. If you're going to make a cheaper product, that's when it's going to be used. Okay. Future research development will be required to reduce the cost of commercial production and fulfill the promise of environmentally friendly garbage bags. Okay. So once we can deal with the cost of it, we can start producing with the bipole, which is useful, which is very useful. They did an experiment, okay, biodegradable plastic bottles made from bipole. This is carried out in Switzerland, okay. Commercially available plastic made from bottles, films, they incubated for 254 days in waters at 85 millimeters. So pretty deep down. Shampoo bottles were positioned precisely on the sediment surface by the use of a small manned submarine. So that's what we went down with a submarine and placed these things on the bottom of the surface, bottom of the lake. Right? And this is the bipole. Okay, a set of bottles attached to the buoy in order to incubate plastic materials in different water depths. So they tried it at the very deep water depths and then shallower depths where they floated them. Okay, a lifespan of 5 to 10 years for this type of bottle was calculated. So into the water, these things live for 5 to 10 years. These bottles exist as plastic. Okay. PHA films are completely degraded, incubated at the top 20 centimeters of the sediment. Okay, in an aquatic ecosystem. Okay, under situ conditions, low temperatures, seasonal variations, plastic goods made from PHA are degraded. Okay, so the regular ones would last 5 to 10 years. These were degraded almost instantly when they put them in the water. So the bipole does work and works very well for the plastic materials. Reactions involving carboxylic acids. Carboxylic acids prepared by oxidation of primary alcohols and aldehydes. Remember, we oxidize primary alcohols. We had to make sure we didn't go too far because we would oxidize into carboxylic acids. We had to stop at the aldehyde stage before. So primary alcohol goes to aldehyde, goes to carboxylic acid. Okay, constantly adding more bonds to oxygen as oxidation occurs. Those are all oxidation reactions. Okay, so there's your primary alcohol, your aldehyde, and your carboxylic acid. Again, so this is ethanol. Okay, we oxidize ethanol into ethanal, which is our aldehyde. We oxidize ethanal into ethanoic acid, which is a carboxylic acid. These are all oxidation reactions. Write an equation showing the oxidation of one propanol to propanoic acid. Again, propanol is 3 carbons, has an OH group of the number 1 position. Propanoic acid is 3 carbons with a carboxylic acid group on the end. Okay. And we can do that by oxidation. We have a middle step. Okay, so here's your propanol, 1 propanol. We oxidize it to propanal. Okay, there's our aldehyde. And we oxidize that to propanoic acid. Okay, We're just taking our oxidation one step farther than we had previously done. So we're taking our primary alcohol to our aldehyde, which we've done before, and now we're taking that further step to carboxylic acid. Okay, everybody see the oxidation that's occurring. You're increasing the amount of bonds to oxygen to make it a more oxidized product. That's oxidation. Okay, synthesis of ethanoic acid by oxidation of the corresponding primary alcohol. Okay, so you want to end up with ethanoic acid. Ethanoic acid has 2 carbons. Okay, that's ethanoic acid. That's what I end up with. So what alcohol do we need to start with? No, yeah. Okay, to oxidize. Their starting alcohol is going to be, it's still going to have 2 carbons. If you're not creating any carbons, you're losing carbons. So you're going to start with CH3, CH2OH. We're going to start with ethanol. Ethanol oxidizes to the aldehyde, ethanal. Ethanal oxidizes to ethanoic acid. That's all the steps involved. Okay. So here's your ethanol. Oxidize it to ethanal. And oxidize that to ethanoic acid. Okay. The easiest way to remember these is you can't change the number of carbons. All we're doing is increasing the amount of bonds to oxygen or the amount of oxygen attached to that carbon. Okay. Butanoic acid to form the primary alcohol. What's the name of the primary alcohol that we're going to start with? If you want to end up with butanoic acid, what alcohol do you have to start with? Carbons stay the same, remember.
Butanol? Butanol?
Butanol, perfect. 1 butanol, exactly. Okay, you start with 1 butanol. Okay, oxidize it to butanal, ALND. Oxidize that to butanoic acid. The easiest way to remember is that you can't change your carbon atoms. So if you got to end up with 4 carbons, you got to start with 4 carbons. It's the only primary alcohol with 4 carbons is butanol. Okay, octanoic acid by the corresponding primary alcohol. So what's the starting alcohol for octanoic acid if you want to oxidize it all the way to it?
Octane.
What are the steps? We start with what?
Octane.
Octane ol. Remember the alcohol?
Yeah.
Octanol. You start with octanol, OL-ending, but you're right, octane is because 8 carbons. So octanol, all single bonds, and the OL means your alcohol. Then you go to octanal, and you're going to go to octanoic acid. Okay. So here's your 8 carbons, just like he said, and your primary alcohol. Okay. That's octanal. That's octanol. Sorry. Okay. And then you oxidize that to octanal, which is your aldehyde. And then you oxidize that to octanoic acid. Okay. Just got to remember oxidation reactions. Now we also can have acid-base reactions with carboxylic acids. Carboxylic acids behave as acids because when they dissolve in water, they deprotonate, which means they give off H+, and they form the carboxylate ion and the hydronium ion. So carboxylic acids give off H+ in the solution. That's a hydronium ion. That's the definition of alcohol. It's one of the definitions of alcohol. An acid. Remember, an acid gives off H+, a base gives off OH-. Those are one of our definitions of acids and bases. Okay. Carboxylic acids are weak acids, dissociated usually less than 5%. So not dissociating a whole lot. So they are weak acids. Okay. So here's a carboxylic acid. Okay. This H is given off as H+. And that's it right here. And it leaves behind the RCOO-. This is your anion. So this is your carboxylate ion right here. Right? And that's what an acid does. Same thing we've done in chemistry before. It's called deprotonation. It gives off a proton, which is H+, into solution. Okay, so there's your carboxylic acid. There's your carboxylate anion and your hydrogen ion. Okay, so carboxylic acid reacts with strong bases to form a carboxylate salt. All right, this is neutralization reaction. An acid and a base form a salt and water. That's why you have an acid spill in the chemistry lab. You neutralize it by pouring base on it. You don't pour more water on it. Okay. So acid proton is removed by the OH group from the base, and it forms water. Okay. Remember, so H plus coming from the acid, OH minus coming from the base, forms H2O. Okay. Equilibrium shifts to the right with removal of H plus by the formation of water. So if this reaction occurs as we form water here, okay, we're removing H plus from the solution because we're forming water. As we remove it, more H plus is produced, so the acid dissociates even further, and it keeps dissociating. So here's your carboxylic acid, and here's your strong base. This gives off H plus, this gives off OH minus. Okay, H plus and OH minus form water. Then you have your metal, which is your positive charge here, and your ion, carboxylate anion. Okay, remember, opposite charges attract each other. So the Na plus attacks to the carboxylic acid that's been deprotonated. Okay. So you got carboxylic acid, you got your strong base, you got your carboxylic acid salt, and you have water. All right. What is the product of each of the following reactions? Look at each reaction. Hydrogen chromate is an oxidizing agent, which means it causes oxidation to occur. Okay, so we got 1-propanol, and we're going to oxidize it. We oxidize 1-propanol, we get propanal, right? Okay, we get propanal. We oxidize it further, and we get propanoic acid. Remember, our primary alcohol oxidized to an aldehyde and then to a carboxylic acid. Okay. So what's the product produced from this? First of all, what is it? What's the name of this thing? Five carbons, aldehyde. So it's pent, 10 al, ALND. We oxidize it, which means we're going to increase this aldehyde to a carboxylic acid. So pentanoic acid. Okay, 5 carbons and our carboxylic acid functional group. I should include that one in there. Okay, so pentanoic acid. Remember, primary alcohols oxidize to an aldehyde, aldehydes oxidize to a carboxylic acid. Okay, now we got a salt, we got a strong base instead of an oxidizing agent. So we're not going to oxidize. What's going to happen? Okay, we're going to pull, this is K plus, OH minus. Okay, so the OH is going to pull that hydrogen off of that acid to make it H plus. H plus combines with OH to produce water. And you get the rest of it's going to combine to produce your CH3, CH2, C double bond O, O minus, your carboxylic anion, and K plus, potassium. Okay, that's going to form your salt. So you're going to form your propanoic acid is going to form your potassium propanoid, okay, plus water. So when a strong base breaks apart, the metal part, the positive charged ion, is going to combine with the negative charge of the carboxylate salt, forming a salt. Barium hydroxide. Okay, barium has a +2 charge, remember? So barium is +2, so OH -1. So there's 2 of them for every barium. Okay? So we're going to lose this hydrogen again, combine with this OH, and we're going to have barium left over with it. So you're going to end up with 1, 2, 3, 4 carbons, right? 1, 2, 3, 4 carbons, O-, and barium 2+. And you need 2 of these because there's only 1 negative charge on it. Okay. So you have to have 2 of the carboxyl anions, barium, which is +2+, and they form 2 waters. 2 hydrogen are taken off, 2 OH groups are taken off. Okay. That's how the metals combined. So salts are carboxylic acid. Okay. How are we going to name these things? We add the cation's name, like if it's sodium or potassium, we say sodium. We drop the ic and add ATE. So instead of propanoic acid, it's propanoate. So it's sodium propanoate, or sodium ethanoate. We drop the ic acid and add ATE. So sodium benzoate. Instead of benzoic acid, okay, we drop the ic acid and add AT at the end. Uses of carboxylic acid. Show some examples of those 2, how to name these things. Carboxylic acid uses soaps like sodium stearate. Okay. Preservatives in foods. Antifungal medications. Those are all uses for carboxylic acids. Okay. They used to control the food pH, how acidic our food is. Okay. So here's an example. This is ethanoic acid reacts with sodium hydroxide to give this compound plus water. So how we name these salts, we list the metal first, the positive ion. So it's going to be sodium. And then we list this as ethanoic acid. Then instead of oic acid, okay, we drop the oic acid and you put ethanoate. So that's sodium ethanoate. We drop the ic acid and added O8. Okay, there's ethanoic acid, sodium hydroxide, and we get sodium ethanoate. Get that, you can see a little bit better. Okay, so we've named the positive charge, the metal first, and then we took in the ethanoic acid and we dropped the ic and added ATE. We dropped the ic acid and added ATE. Okay. All right. Everybody remembers how to name this one. What's that name?
Benzoic acid.
Perfect. That was benzoic acid. Okay. Sodium hydroxide. Then we form water. And then this one here forms. So this is benzoic acid. To name the salt, we name the metal first, which is sodium. And then we take benzoic acid, we drop the ic acid and add O8. So sodium benzoate. So benzoic acid. Okay. Reacts with sodium hydroxide to give you sodium benzoate. Get rid of that so you can see the. Okay, perfect. So the salt, does someone have a question? Okay, so the salt of carboxylic acid is named by replacing the ic acid with ATE. So ethanoic acid becomes ethanoate. Benzoic acid becomes benzoate. And the name of the cation is put in front of it with its sodium, potassium, barium, calcium, whatever the name of the metal is, whatever the name of the positive ion is, you put that in front of it. And that's how you name these things. Write an equation for the neutralization of propanoic acid by potassium hydroxide. Okay, so you're going to write the equation now. Propanoic acid is 3 carbons. Okay, propanoic acid. And we're going to add potassium hydroxide. Strong base. So you know OH minus from here is going to react with the H plus from here to form water. And what's going to happen is going to pull this H off of here. So you're going to have CH3, CH2, CO minus, and potassium plus. Okay, so there's your reaction. There's propanoic acid. Okay, it takes that H plus, combines with that OH minus to give you your water. Then the K plus reacts to the negative that's left by here. Okay. So the product would be potassium propanoate. Okay, you drop the ic acid. Okay. Write the formula for the organic product obtained through each of the following reactions. Okay. So the organic product is not water. So it's going to be the other one. It's going to be again, the easiest way to do it is count the number of carbons. There's 3 carbons on the left, there's going to be 3 carbons on the right. So it's going to form, I didn't want to go. I went back way too far. Let's see, I can bring it right back here. Okay, this should be it. Yep. All right, so 3 carbons. So your answer is going to have 3 carbons. Okay, there's an alcohol. You've lost your O. So there's a negative charge, and this is potassium. Okay. So that's what you get. That's your organic product. 3 carbons again. There's your carboxylic acid group. The hydrogen's gone. So it's left a minus charge behind because the hydrogen was plus. So left a minus charge behind, and the potassium is positive. So it combined with it. Right? So that's your organic product formed from the reaction. Okay, same thing again. You're going to have 1, 2, 3, 4 carbons. So butanoic acid, and it's going to combine with 2 OHs here because barium has a +2 charge. Okay, so you're going to have this compound 2 times because there's a -1 charge and barium's a +2 charge. The charge have to balance. So it loses a hydrogen to form water, and it gets replaced by the metal and ion. Okay. Again, 6 carbons, you're going to end up with 6 carbons. Same carbon chain. That's exactly the same. And you can have that minus charge because you've lost this hydrogen. You've lost this hydrogen right here and this OH, and you're left with K plus. So potassium and then 6 carbons attached to it for your carboxylic acid. Okay, that's how carboxylic acids form salts. Benzoic acid. Remember, benzoic acid is a benzene ring. Conjugated double bond system. Every other bond's a double bond. And benzoic acid is COH. And this is the H right here we're going to lose and give this negative charge. And there's your benzoic acid. You've lost the hydrogen. Okay, now we have a negative charge there. And then we added the sodium from the sodium hydroxide. The hydroxide combines with the hydrogen to produce water. The sodium combines with the benzoate anion. Okay. So now let's name the insult we just produced. We use all those things. Let's name them. This is the first one. What's the name of this thing?
Potassium.
Okay. First, go ahead. Someone's going to name it. First thing you name is a metal, the positive ion, the cation. So it's potassium. So potassium, and then 3 carbons. So it's pro, pan, O. And instead of oic acid, it's ATE. So potassium propanoate. Okay. Next one. What do we name first?
Barium.
Perfect. Barium. And then 1, 2, 3, 4 carbons. So what would you name the second part?
Butanoate.
Butanoate. You got it. Perfect. That's exactly right. So it's a barium, butanoate. You drop the ic acid and added ATE. You get rid of the ic acid. And butane is 4 carbons. Okay, what would that one be? What's the first name?
Potassium.
Potassium. Then you got 1, 4, 5, 6 carbons. 6 carbons is hexane. So potassium, hexanoate. Potassium hexanoate. Okay, last one. I think it's the last one. Okay, what do we name first? Sodium, right?
Sodium.
Sodium. And this is benzoic acid. Here's your benzene ring. So this is benzoic acid. So we drop the IC, add OAT. So sodium benzoate. Okay. So carboxylic acid salts are ionic substances. Remember, we have a metal positive charge. Then we have the anion from the carboxylic acid. So they're ionic substances. They're water soluble. Ionic substances are water soluble. The long chain carboxylic acid salts, the free acid salts, are called soaps because if the carbon chain gets very long, remember there's a long carbon chain. Let's do the line structure. Okay, that's your carboxylic acid salt. That's your carboxyl salt. Sodium, how many carbons that is. Okay, as this chain gets longer, this chain becomes non-water soluble. This part is soluble. This part is non-soluble. That's the long carbon chain. Okay, so the head of it is soluble, then the body can be non-soluble depending how long the fatty acid chain is, the number of carbons it has on it. Okay, so esterification. Remember, esters are R, C, O, O. Okay, now instead of having an H here for carboxylic acid, we have another R group. It doesn't have to be the same one. That's an ester. So esterification is creating esters. So carboxylic acid react with alcohols to form esters. Okay, so we're getting it. So we're not oxidizing now. Okay, carboxylic acids, once they're formed, are going to react with an alcohol to form esters. Okay, it's going to give you another oxygen in there. And it's going to form water as a byproduct. So here's your carboxylic acid. Follow what's going to happen here. And this is your alcohol. Okay. The hydrogen gets lost on the carboxylic acid. The OH group gets lost on the alcohol. These two link together to form water. Okay. This leaves your R group and it bonds to the oxygen right there. So here's your carboxylic acid part, and there's your R2 from your alcohol. Right? It's a dehydration reaction. The bond is formed by removing water from between the two, just like we do with the polymers, with the bipolar for the trash bags. We did the same thing with lactic acid. It was a dehydration reaction. Dehydration reaction is very common in organic chemistry because water is so stable. Okay? It's extremely stable. It wants to form water. It's a very stable compound. Okay? So here's your ester, your R. This is your carboxylic acid group, and this is a group from your alcohol. So RCOO and another R. That's an ester. That's esterification. So you can form an ester from reacting a carboxylic acid with an alcohol. Carboxylic acid, alcohol, and your ester. Okay. Structure and physical properties of esters. They're mildly polar. They have some polarity because they have that carbonyl group. But now that they don't have the hydrogen to give us, there's no hydrogen bond like carboxylic acids have. So they're somewhat polar. They're not as polar as carboxylic acids. Okay. Frequently found in natural foodstuffs. Okay. They have a pleasant aroma. They don't smell like the carboxylic acids did. Okay. Isoamyl acetate is a ester, and it's a banana oil. 3-methylbutyl ethanoate. Okay. Ethylbutanoate. Okay, is pineapple aroma. Isobutylformate is raspberry aroma. So it smells like a lot of fruits. Okay, it's got a pleasant smell to it. Isobutylmethanoate. Okay, they boil at approximately the same temperatures as carbonyl groups with comparable molecular weight. It's going to be roughly the same temperature they boil at because they do not have hydrogen bonding like the carboxylic acid. And we're going to name them just like we name the salts. Same way. Okay, or very similar way. Esters form reacting carboxylic acid with alcohol, which is reflected in its name. The alkyl group, okay, as the first name. That's the alcohol part of the ester. That's going to be our first name, just like the plus was of the other one, the cation, the ion, positive charge ion. We base the name of the acid part of the structure from the longest carbon chain ending in the carboxyl group. Okay, that's the carboxylic acid part of the ester. So you have two parts. One part that forms from the alcohol, one part that forms from the carboxylic acid. Okay, we change the ic acid to ATE, just like we did before. So we drop the ic acid and add ATE. So here's our carboxylic acid. Okay, this is 2 carbons, so it's ethane, ethanoic acid. This is 1 carbon for our alcohol. So this is methanol. Okay, there's your alcohol and there's your carboxylic acid. They combine, remember, you lose this H and this OH. So now the CH3 is going to attach to that O group, which you have right here. Okay. So we're going to name that group first, then the acid. So this is ethanoic acid. That's methanol. Okay, when we put together, we're going to drop the group. We call methyl ethanoate. So methyl is what we added from the alcohol. Ethane was what we added from the carboxylic acid. And then we drop the IC acid and put O8. So methanoate instead of methanoic acid. So that's where we react. We react an alcohol and a carboxylic acid to produce an ester. And we name it by naming the attachment from the alcohol. Okay. And then the rest of the carboxylic acid, dropping the ick and adding O and adding ATE. Okay. So name the following esters. We know how to form esters now. Esters are formed by an alcohol and a carboxylic acid. Okay, so if you look at this thing, you can easily see where the carboxylic was formed from. Remember, we took the H off the carboxylic acid, and we took the OH off the alcohol to form water. Now we're gonna name it. We're gonna name this, just like we had this in like sodium plus and this O minus, okay? So it's the same type of deal. We're gonna name it the same way. We name this first, and then drop the ick acid and add ATE. So I want to get rid of my lines. I want to get rid of the sodium. Okay, perfect. Okay, so what are we naming first? We're naming the part from the alcohol, which is the part that attached to the oxygen of the carboxylic acid group. So this is ethyl. That's this right here, 2 carbons. And this one is 1, 2, 3, 4 carbons. So ethyl, butane, and instead of we had oic acid for our carboxylic acid, we dropped the ick acid. So it's ethyl, butane-O, and then we add ATE. Okay, so ethyl butanoate. Let me move it out of the way so I don't get rid of, you can see some of the other writing here. Okay, so the alkyl portion from the alcohol is ethyl, just like we said. Okay, so here's your alcohol right there. So that's ethyl. Then this is butanoic acid. Okay, we drop the ick acid and we put in ATE. So ethyl butanoate. Okay, same thing we did with the metals. So don't get confused. Instead of adding a metal group now, we're adding the part of the alcohol. And we're naming that first. All right, so this one. How many carbons does the alcohol portion have of this ester? Someone want to tell me? How many points does the alcohol chain have?
1,
No.
2,
No. Keep going. You got one more choice.
3.
3. Perfect. This is the alcohol section right here. Remember, this is your carboxylic acid. So this is the alcohol portion that's added. That's what we're going to name first. There's 3 carbons to the alcohol. So the starting alcohol was propanol. Propanol was mixed with ethanoic acid to produce this ester. And we're going to name the alcohol portion first, which is 3 carbons. So it's propyl. It's our attachment. Just so we had to a long chain hydrocarbon. That's propyl. And then the acid was ethanoic acid. And we're going to drop the ick, ethanoic, and we drop the IC acid and adding ATE. So it's propyl ethanoate. Okay. So the alcohol portion is the propyl ethanoic acid. We drop the ick acid. And we have the ATE ending. Okay. So if you look at it, you can reconstruct it. Once you see 8, you know it's an ester. You know, there's 2 carbons on the carboxylic acid side, and there's 3 carbons on the alcohol side when it was formed. So it's propyl ethanoate. Okay. It's the exact same thing we're doing for the salts and carboxylic acids. So instead of naming sodium, we just name the attachment now. Whether it's 3 carbons, 4 carbons, or whatever, we're going to name the attachment. So reviewing it, this would be sodium, ethane, OH. Okay, we put this one first, and then we take the OH from the ick acid. Yeah. Okay. So we always name this part first, whether it's an attachment or the carboxylic acid salt. Okay, same thing. This is a carboxylic acid. It's the exact same thing we got right here. Exactly. So now there's a negative charge on the left one. So instead of sodium ethanoate, we name the attachment from the alcohol, which is 2 carbons. So this is going to be ethyl, because we're going to name the attachment. And there's 2 carbons for the carboxylic acid. This name is exactly the same, ethanoate. Okay, so this name stays the exact same, ethyl, ethanoate. So instead of naming the metal, instead of calling it sodium, now we call it by the attachment. I attach it to it. It's the exact same system. We're not putting anything new in here. So the alkyl person first name is ethyl. The parent carboxylic acid is ethanoic acid. So we drop the ic acid and we put in ATE ending. So ethyl, ethanoate. Okay. The molecule shown below is the characteristic flavor of apricots. Okay. That's what gives you your apricots its flavor or its smell. Okay. So we need to name that thing since we like apricots. Okay. How many carbons does the alcohol portion have? The part that's attached from the alcohol. How many carbons does that have? Someone, did someone say 5?
5 pentyl.
You got it. Perfect. Exactly right. This is the alcohol portion that's attached. So 1, 2, 3, 4, 5 carbons. So like I said, it's pentyl. So the first name of this is going to be pentyl. Okay. Then we name the carboxylate anion, which you just did before. So there's 1, 2, 3, 4 carbons. 4 carbons is butane. So that was butanoic acid. We dropped the ic acid and butanoate. Butan O, drop the ic, add ATE. So pentyl, butanoate. Now going backwards, if they gave you the name, how to draw it. Okay, you have 4 carbons, butanoate. This is a carboxyl salt. There's 4 carbons, okay, and it ends in OATE. And that is your carboxylic acid. So you know it's an ester, and it's going to attach to the alcohol of 5 carbons. Name each of the following esters using the IUPAC name. All right, let's name this thing. So how many carbons on the alcohol portion?
Three.
Propyl.
Perfect. Yep, 3 carbons, and it's propyl. Very good. Okay. This is your alcohol portion, so it's going to be propyl because it's an attachment, just like if it was attached to a carbon chain. Same of the things we've been doing. So propyl, and then how many carbons on the carboxylic acid? There's 4, right? So it was butanoic acid. We drop the ic acid and add butanoate for the ester. So it's propyl butanoate. Okay, 5 carbon alcohol from the alcohol, 3 carbons from the alcohol, I'm sorry. So we know the alcohol was propanol, and then 4 carbons on the carboxylic acid part for the ester. Remember, esters have 2 parts, carboxylic acid side and an alcohol side, because they're formed by the dehydration reaction between a carboxylic acid and an alcohol. All right, name this thing. Again, the easiest way to do this is to divide it. Just draw a line, divide it. Here's your alcohol portion. Here's your carboxylic acid portion. The alcohol portion always is named first as an attachment. There's 2 carbon, so the name for a 2 carbon attachment is, what's the name for a 2 carbon attachment?
Ethyl.
Perfect. That's called ethyl. And then you've got 1, 2, 3, 4 carbons here. Butanoate. You drop the ic acid. So ethyl, 2 carbons for your alcohol, and then butanoate, 4 carbons from the carboxylic acid. Ethyl butanoate. Okay, and this one, Again, once you got your division, you're perfect. There's your dividing line. This side comes from the alcohol. This side comes from the carboxylic acid. Okay, so this is our attachment. We have three. This is propyl. Okay, and this is 2 carbon, so ethanoate. Propyl ethanoate. Okay. Again, division line, alcohol, carboxylic acid. So the alcohol has 1, 2, 3, 4 carbon, so it's butyl. The carboxylic acid portion has 3, so it was propanoic acid. Drop the ic, drop the ic acid, put in ATE, so propanoic acid, butyl propanoate. Reactions involving esters. Okay, we formed esters by reacting a carboxylic acid and an alcohol. We can tell the alcohol portion and the carboxylic portion, and we name it by identifying the alcohol portion first, and then name the carboxylic portion, dropping the ic acid and putting ATE. Those are our esters. Okay, so how do we prepare esters? Carboxylic acids react with alcohols. That's what we've been doing. That produces esters. Okay. The reaction is catalyzed by a strong mineral. Heat is required. A water molecule is released. So it's a dehydration reaction. Like I said, a lot of these reactions are dehydration reactions because water is such a stable molecule. It's a driving force. When water formed, it's so stable that it draws the reaction in that direction. That's why a lot of our organic reactions are dehydration reactions, just like our polymerization reactions. We get rid of water. So here's your carboxylic acid. Here's your alcohol, and it forms the ester and water. This is the alcohol part. This is the carboxylic part. Okay, so R2, right here, R2 came from the alcohol. It's the part attached to the oxygen from the carbonyl group. Okay, that's what we've been doing. So the same thing we've been doing here. So methanol reacts with propanoic acid to produce water and our ester. Our ester is, here's a dividing line, right? This side is the alcohol part. This side was the carboxylic acid part. Okay, so this is methyl. And then the alcohol part was propanoic acid. We dropped the ic acid, so propanoate, methyl propanoate. I don't know if I was going to say that or not on here. No. So I'll go back one slide. So again, this was methyl. Propan O, and we drop the ic acid and put 8. Okay, so carboxylic acid reacts with an alcohol in the presence of a mineral water and heat or an acid to produce an ester. We name the ester by the alcohol portion first as a substituent, as an attachment, and then we name our acid portion by dropping the ic acid and putting ATE on the end. So write an equation now showing the esterification reactions that would produce ethyl butanoate and propyl ethanoate. Okay, so two questions here. You want to produce ethyl butanoate. So to produce it, you got to know what that is. So we work backwards in organic chemistry like we always have. So butanoate. Butanoate, if we reverse it, came from butanoic acid. Okay, butanoic acid is 4 carbons. Okay, there's butanoic acid. Okay, so we got rid of the H. Get rid of the H. Okay, and it was the alcohol. The alcohol was ethyl. CH2, CH3. So that's ethyl butanoate. That's what we have to form. So what alcohol are we going to start with to form ethyl butanoate? What's the alcohol?
Ethanol.
Perfect. Alcohol is ethanol, 2 carbons. So we're going to have ethanol, It's going to have to react with what's the carboxylic acid we're going to use?
Butanoic.
It's going to be perfect. Exactly right. Butanoic acid. You got it. And right here, the ethyl is our first attachment. So we need ethyl alcohol, which is ethanol. And then butanoate is butanoic acid. So here's our ethanol. That's our alcohol, the 2 carbons. And then this is butanoic acid, our 4 carbons. Okay. And that reacts to form ethyl butanoate. There's your reaction. Okay. So here's your alcohol. Again, here's your division line. There's your alcohol. And there's your carboxylic acid. Okay. So to form ethyl butanoate, we have to start with ethanol and combine it with butanoic acid. Okay. Next one, propyl. Well, I don't want to go that far. I'm going to say, yeah. Okay. We'll bring it back here. Okay. Next one is propyl ethanoate. Okay. So we got to start with the first one's the acid. So we got to start with propanol, which is 3 carbons. And we got to end, and we got to have the carboxylic acid with ethanoic acid with two carbons. Okay, so propyl ethanoate. Ethanoate is 2 carbons. And then propyl is 3 carbons. Okay, so that's propyl ethanoate. So just looking at the name or looking at the structure, either way, you know propyl is 3 carbons. That's our alcohol. So propanol. And ethanoate is 2 carbons. That's our carboxylic acid. So here's our alcohol. Propanol, 1 propanol. Okay, 3 carbons. And here's our carboxylic acid, 2 carbons, ethanoate. And it's going to form what we just drew. Okay, it's going to form propyl ethanoate, and water for a balanced reaction. Remember, it's just a dehydration reaction where we're losing the H from the carboxylic acid because that's what acids do. They lose hydrogen. They don't have hydrogen in this solution. And then we lose the OH from here. And this carbon here is going to attach to that oxygen. That's how they're formed. During this reaction produces butyl ethanoate and ethyl propanoate. So first one is butyl ethanoate. So butyl ethanoate comes from butanol, because you always name your alcohol first, and ethanoate comes from ethanoic acid. Okay, those are our 2 compounds right there. So we're going to react butanol with ethanoic acid, and that will produce butyl ethanoate with a dehydration reaction. You should put plus water on the right-hand side, but we don't have that. So this is butanol. 1, 2, 3, 4 carbons. This is ethanoic acid. Okay, and this is butyl ethanoate. Can everybody see why I divide it right here all the time? Give me a thumbs up or something. If you understand why I draw a line there when I'm naming this thing, to give you the alcohol part and the carboxylic acid part.
Yeah.
Okay, perfect. Okay, that's once you identify that, then the rest is straightforward. Okay, next one is ethyl propanoate. So ethyl is the acid, so it's ethanol. And propanoate is from the carboxylic acid. So it's propanoic acid. Those are 2 starting components, ethanol and propanoic acid. So here's your ethanol, and here's your propanoic acid. They come together. This loses H. This loses OH. This carbon attaches to that oxygen, and you produce water. While you're producing ethyl propanoate. Again, your dividing line is right there. Okay. Design the synthesis of ethyl propionate from organic alcohols. Okay, so now we got to start with two alcohols. Okay. So one alcohol is easy. There's ethyl, so we got to start with ethanol. That's an O. That's an A. Ethanol. Ethanol, sorry. Okay. And then we have to find out propanoate. So we have to produce propanoic acid. Now, how can we make propanoic acid from an alcohol? Remember the first part of the lecture? Oxidation of an alcohol produces an aldehyde. Oxidation of an aldehyde produces carboxylic acid. So we're going to start with propanol. Propanol oxidation goes to propanal. Oxidation goes to propanoic acid. Then we combine propanoic acid and ethanol to get ethyl propanoate. So you're going to start everything from alcohols. Okay. So here's our one starting material. Here is this is what we have to produce, right? Let me get rid of some of the marks here because there's a lot to this one. All right. So design the synthesis of ethyl propanoate. So how do we make ethyl propanoate from alcohols? From two different alcohols. Okay. So this is what we want to end up with. This is ethyl propanoate. Okay. So produced by the combination of propanoic acid and ethanol. Okay. First form propanoic acid from propanol by oxidation. Where we have to start from alcohols. You can't start with carboxylic acid. So propanol. Okay. Propanol undergoes oxidation to propanal, your aldehyde, undergoes oxidation to propanoic acid. Okay, so now we got propanoic acid. And we can combine that with ethanol. Okay, combine propanoic acid with ethanol. Okay. And that forms your ethyl propanoate. Here's your ethyl group and your propanoate. Because here's your carboxylic acid and there's your alcohol. So the two starting materials were, number one, propanol, and we produced, from propanol, we produced that carboxylic acid. So we've used two alcohols to produce an ester. We took one alcohol, oxidized it to an aldehyde, oxidized it to a carboxylic acid. Then we combine that carboxylic acid with the other alcohol to produce our product, okay, ethyl propanoate. Okay. That's how we can design different drugs and different things by knowing what we're starting with, what we want to end up with. Okay. Design methyl butanoate from organic alcohols. Again, we're going to have methyl butanoate. Methyl has one carbon. So the alcohol we use for that is methanol. Butanoate. Okay. We need 4 carbons. So we start with butanol, which is our alcohol. Oxidize it to butanal, which is our aldehyde. Oxidize that to butanoic acid. We can combine the butanoic acid with the methanol to produce methyl butanoate. That's the steps you're going to do. So here's our compound. Again, here's our dividing line. This is the alcohol portion. This is the carboxylic acid portion. So there's methyl butanoate. Like we said, we're going to start with butanol. There's butanol or alcohol. We oxidize it to butanal, or aldehyde. Oxidize that to butanoic acid. We're going to combine butanoic acid with methanol. Here's our methanol, and this is our butanoic acid. Okay, and that's going to give us an ester. We're going to lose H here. We're going to lose OH here, and that oxygen is going to combine to that carbon to give us methyl butanoate. So we can synthesize any ester we want from 2 alcohols. We just have to oxidize one first to its carboxylic acid. And then we can round carboxylic acid with the alcohol to produce an ester. Okay, let's make propyl. methanoate. Okay, so think about it. Propyl's the alcohol portion, so I need propanol, what we start with. Okay, propanol is going to react with our other carboxylic acid. So methanoate has to start from methanol as an acid. Methanol goes to methanal. Methanal oxidizes to methanoic acid. Methanoic acid can react with our propanol to produce propyl methanoate. We do the same thing. This is propyl methanoate. Again, here's our dividing line. So this is your alcohol part. This is your carboxylic acid part. So the alcohol part, we have to form this carboxylic acid part. So we take methanol, oxidize it to methanal, oxidize that to methanoic acid. Now we got a carboxylic acid, and then we got our alcohol, which is propanol. Okay, that was our name right here. So we take propanol, react with our alcohol to get our ester. Okay, so methanoic acid plus propanol gives us propyl methanoate. Again, this is our alcohol portion. This is our carboxylic acid portion. That's what carboxylic acid was, 1 carbon, and that was our 3 carbons to give us propyl methanoate. I'm gonna keep saying it backwards. Okay, so that's how we can synthesize an ester from 2 alcohols. Okay, flavor and fragrance. Carboxylic acid smell bad. We talked about it before. Some of the butyric acid was the butter that came out, or a gangrene smell from your patients. It can be really bad. Okay, so when we change carboxylic acids by reacting with alcohols to esters, we change the smell to a lot nicer fragrance. Okay, so butyric acid is also a product of fermentation reactions carried out by Clostridium perfringens, which is your gangrene, causes gangrene. Or the most common cause of gangrene in the body. So butyric acid contributes to the notable foul smell accompanying this affection, and they really do smell bad. By forming esters of butyric acid, you can generate compounds that smell pleasant. Okay, so ethyl butanoate instead of butyric acid is pineapple oil. Okay, pineapples smell a lot different than gangrene. A lot different. Okay, so here's how we did it. This is butanoic acid. Okay, react it with ethanol, and we end up with ethyl butanoate. So we take from gangrene smell or rancid butter smell to pineapples. Raspberries. Okay, methanoic acid. Okay, and we've got 2-methyl propanoic, 2-methyl propanol. Okay, so this is 2-methyl propanol here. I don't have the names on this one or not. No, I don't. So 2-methyl propanol. Okay, and it reacts to form this compound right here. Okay, so how would you name that ester now? Because this is the alcohol portion. This is the carboxylic acid portion. Okay, the alcohol portion is 2-methyl propyl. That's the first name, 2-methyl propyl, because this is your attachment. This is your number 1 carbon, then number 2, then number 3. Okay, so 2-methyl propyl, and then this is methanoic acid, so methanoate. So 2-methyl propyl methanoate. Okay, you always name your alcohol portion first, and then name your carboxylic acid portion, dropping the gic acid and putting ATE. Okay, this is the smell of bananas. Okay, this is ethanoic acid. Okay, and this is your alcohol. So here's your division line. Name your alcohol, name the alcohol portion first. So this is 1, 2, 3, 4 carbons. So it's 3 methyl. And then 4 carbons is butane. So 3 methyl butyl. And the next word is, there's 2 carbons here, ethen. Oh, instead of ic acid, we drop that and put ATE. So 3 methyl butyl ethanoate. Okay, always in your alcohol portion first. And that's the side that's attached to this oxygen from the single bond. Okay. Again, for apples, this is methyl butanoate. Okay, you combine methanol and you can find butanoic acid. So again, you went from a very foul smelling compound to one of apples. Okay. Where we at? So this is ethanoic acid. And this is 8 carbons, so octanol. Your OL is your alcohol. Okay, so here's your alcohol division. 8 carbons. Okay, so octanyl, can't say that. Octanyl. So this is octane. So octanyl or octyl. Octanyl ethanoate. Octyl, too many letters in there. Octyl, I'm sorry, getting confused. So octyl ethanoate, 8 carbons. Okay, and pentyl butanoate. Okay, you're taking butanoic acid, real bad smell, put it to apricots. And this is, you have 5 carbons here, so this is pentyl, and then butanoate. Okay, so you more nicer smell. Strawberries. Okay, strawberries are a little bit different because this is a thiol group now. This is an SH group here. Remember, if it's OH, it's alcohol. If it's an SH, it's a thiol group. So this is methyl. Okay, because here's your alcohol portion. Still methyl, and this is your thiobutanoate because it's an S instead of the oxygen now. So your attachment group is methyl, but this is a thiobutanoate. Okay. Hydrolysis of esters. Okay, main reaction by esters is hydrolysis, reaction with water. Okay, now you do hydration. You're going to add water to an ester. When you add water to an ester, it's the exact same opposite of dehydration. So when you add water from an ester, you're going to form your carboxylic acid and your alcohol back. Okay, so it requires heat. Mineral acids used as a catalyst. So we're taking our ester and we're going to break it apart. We're going to break it back into a carboxylic acid and an alcohol. Just got to keep everything straight. This part here is going to form the alcohol. This part here is going to form the carboxylic acid by adding H, and the other one you're going to add OH. So this will always add an H. This will always add your OH, not the other way around. Okay, so you got to make sure you add the right part when you're doing hydration reaction. Okay, so the acid hydrolysis will be a carboxylic acid and a alcohol. Because a carboxylic acid alcohol formed an ester, when you break it apart by adding water back to that bond, okay, it's going to form back your carboxylic acid and your alcohol. So here's your ester. Remember a dividing line. It's going to be the exact same. So learn how to do that. This is going to be the alcohol. This is going to be the carboxylic acid. Okay. This is going to add H plus. This is going to add OH. So it's going to be CH3, CH2, CH2OH. So you can add the OH right to here. And you add the H right to here. Okay. So that produces propanoic acid and propanol, 1-propanol. Base hydrolysis of esters. Okay. Base catalyzed hydrolysis of an ester is what's called saponification or soap making. Okay. The products are going to be the acid salt, like we talked about before, and the alcohol. So we're going to form a carboxylic acid and an alcohol, just like I did before, except now it's going to be the presence of a base. So a base takes the proton off of the carboxylic acid and forms a carboxylic acid, carboxylic salt. Okay, just like we did before when we had them. Okay, acids cannot exist in basic conditions because the H plus is pulled off. So the product is the salt of the carboxylic acid using the cation of the base catalyst. So if the base is sodium hydroxide, we have sodium ethanoate or sodium propanoate, whatever we have left on the other side for the carboxylic acid. Okay. So here's the ester. Okay, we're going to add water. So we're going to hydrolyze it. So we're going to get the alcohol plus the carboxylic acid, and the carboxylic acid in the presence of a base. The base pulls the H plus off, and the metal ion attaches from the base to the carboxylic salt now. Okay, just like we did at the beginning of the lecture. Same thing. So if we had, again, here's your dividing line. This is 1, 2, 3, 4 carbons, so it's butyl. So butyl ethanoate, and we're going to add heat in the presence of a base. So we're going to hydrolyze. We're going to add water back to it. We're going to add the H to here. We're going to add the OH to there. So we get our alcohol. There's our butanol. And we get our carboxylic acid. Now the carboxylic acid is in the presence of a base. The base pulls the proton off. So the carboxylic acid formed is going to be right there like that. The base, sodium hydroxide, pulls that off, reacts with the OH here. That forms water. And you get this carboxylic salt with the sodium part. And you get sodium ethanoate. Okay. So whenever there's a base and the carboxylic acid is formed, it's going to give you the carboxyl salt. Okay, because the proton to H is going to be pulled off. Okay. Now, in the presence of an acid, we'll put the H back on. So in the presence of a base, that H is pulled off. In the presence of an acid, because acid is donating a proton back, that's a stronger acid. So the H from this acid is going to go back and protonate the carboxylic acid. So now you get ethanoic acid and then NaCl for your sodium chloride, for your salt. Okay. So a carboxylic acid, which is a weak acid, is in the presence of a strong base. Okay. It forms a carboxylate salt. So like sodium ethanoate here. If a carboxylic acid is in the presence of a strong acid, it forms the carboxylic acid. Okay. Because the acid adds the H plus back to the carboxylic salt. The base pulls it off. Okay, so complete each final reaction by drawing the structure of the missing products and name each one. So what will this form? Okay, you're going to add water. So you're going to add OH to here. You're going to add H to here. And you're in the presence of an acid. So what's it going to form? It's going to form the alcohol, which is CH3, CH2, CH2OH, right? Propanol, 1-propanol. And it's forming the carboxylic acid, CH3CO, ethanoic acid. Okay, so it's going to form the acid and it's going to form the alcohol. Why does it not form the carboxylate salt? Okay, because there's no strong base to pull this H off of here. Instead, this acid H plus is going to protonate that back on there. So in the presence of acid, you're going to form ethanoic acid. Okay, and you're going to form 1-propanol. Does that make sense? So far, so good. Okay, same thing. Now we're going to be in the presence of a strong base, and the delta means heat. So strong base and heat. Again, you're going to add water. It's a hydration reaction. So hydrolysis, you're going to add water to it. The OH goes here. The H goes here. So the acid you're going to form is going to be CH3, CH2, CH2, OH. And the carboxylic acid you're going to form is 6 carbons. So 6 carbons, double bond O, and OH. Now you're in the presence of a base. So this H is going to be pulled off to form water, and you're going to replace that with what basically a potassium. Okay. So what you're going to end up with is the carboxylic salt, because you're in the presence of a base, it pulls the H off of there, and the alcohol. Boy. So name the salt. You name the first metal first, so potassium. And there's 6 carbons. So potassium, hexane, O8. You drop the ic acid. So potassium, hexanoate, and the alcohol is 1-propanol. There's 3 carbons. Okay. So you got to remember there's going to be a different product formed in the presence of an acid versus the presence of a base, because how the carboxylic acid reacts to it. All right. Again, you're adding water and your presence of a base. So here's your alcohol. This is your alcohol side. This is your acid side. And you're going to lose the hydrogen that you added. You add a hydrogen here, OH here. You're going to lose this hydrogen, and you're going to replace it with sodium. Okay. So in the presence of a base, you get sodium in the presence of in place of the hydrogen, and you get your alcohol. So the product is going to be sodium. And how many carbons we have? 5 carbons, so pentyl. So sodium pentanoate. Okay. And the alcohol is going to be methanol. 1 carbon. Okay. And give you another example here. There's your dividing line. You're in the presence of an alcohol, of an acid. So it means you're going to form your alcohol. You're going to form your carboxylic acid. And then you're going to form your alcohol. So this is going to form the alcohol. This is going to form the carboxylic acid. You're going to add an H here and an OH there. Okay. And that's what you formed. So you have formed, how many carbons here? 4, 5, 6 carbons. So this is 6 carbons. So hexanoic acid. Okay. The other one's going to form is going to be 1-methyl, 4 butan. To be 1-methyl, 1-butanol. Or 2-pentanol. Oh, I'm sorry. It's the longest carbon chain. There's your longest carbon chain. I got confused on it. Easy to make mistakes. So watch it on your tests. Here's your longest carbon chain. It's just written at an angle. So 1, 2, 3, 4, 5 carbons. OH group is attached to the number 2 carbon. So it's 2-pentanol. Sorry about that. Okay. So your OH here is attached to the number 2 position. Okay. Saponification, making soaps. Okay. That's what saponification means. It's a base catalyzed hydrolysis of fats. That's how you make soap. You use fats. This is fat here. Okay. This is your triglycerides. This is fat or oil. Okay. It's a carbon chain. And there's a mistake here. That should be CH, not CH2. There's too many bonds to carbon. Oh, wait a minute. No, that's not right. Okay, this is your, play that again. This is your fat back here. This is your triglyceride. Okay, these are esters. Okay, you can see the alcohol portion here, carboxyl portion here. Okay, so this bridge forms your alcohol portion. So when you hydrolyze it to make soap, you're going to add your OH from the water here, and you got an H onto this one, and it's in the presence of an acid, so you're going to get your metal, sodium, potassium, whatever it is, combining here to form your soap. Okay, that forms glycerol, and this forms your soap right here. This is a mixture of carboxylate salts. Okay, so it's in the presence of a strong base, and whatever the metal is, potassium, sodium, barium, calcium, whatever your metal is what's going to appear here. Okay, and that's going to form your carboxylate salt, which is your carboxylic acid salt, which is your soap. Okay, anyone see the movie Fight Club? Yep, great movie. It is the best chemistry accurate movie ever done. It's phenomenal. When they made soap from stealing from a liposuction clinic. They went in, they stole the fat that sucked out of people, and they made soap from it. And they sold the soap, put their proof on it, and they sold the soap. The byproduct is glycerol. Okay. Glycerol they used to make nitroglycerin. And they used ammonia to do it. That's all you got to do. This is glycerol here. Nitroglycerin is put an NO2 group here. NO2 group here. Get rid of the hydrogen. Just put NO2 here. Now you got nitroglycerin. Okay, and they use that to blow up the city block. That's exactly how you do it. You use fat. You break it down to make the soap. The byproduct is glycerol. Okay, and use that to make nitroglycerin. Very simple procedure to do. But that's how you use this process we're doing, the saponification or the hydrolysis with the base to cause, I'm getting a low battery. Let me plug this in real quick. Or else I'm going to lose my charge here on this thing. Where is it? Okay, we're good. I think we're good. All right. So that's how you make salts. That's how we use it. Okay. And the metal can be sodium, potassium, whatever metal we use. Okay. So this is what happens. You have a carboxylic end, which is soluble in water. Then you have these long chain fatty acids, which are not soluble in water. So when you put it in water, you have like an oil stain or something like that. The fatty acid chains bond to the oil stain, like you're using it for dishwashing or soap or anything like that. The fatty acid chains bond to the non-soluble part, which is the oil. And then the carboxylic acid chains are soluble and it lifts off the oil stain or whatever. That is not polar. Okay. So the wiggly lines represent the long carbon chains of each soap molecule. So particles of oil and grease are surrounded by soap molecules and they form what's called a micelle. And these micelles migrate away from it. Okay. And lift off of fabrics and things like that. And that's how soaps work. Okay. By combining the two ends, the one end that's non-polar and the other end that is polar. Okay. Polyesters are condensation polymers. So polyesters are these polymers that are these long chains. They're eliminating a small molecule like water, like dehydration reactions, like diacid or diol. Each combining molecule has two reactive functional groups. So when you combine it, there's two reactive functional groups. You can see that there's a OH group on both sides. There's a carboxylic acid group on both sides. Okay? So when you combine them, you can link between the two functional groups. So you can form a link here, and then use the other side to form another link and so on, and form your polymer. Okay, this is polyurethane. Okay, that's how polyurethane is formed. You continue condensation at each end because each end has a functional group. Okay, this is polyethylene terephthalate, which is called PET. Okay, it's used in Mylar, plastic bottles, polyester fabrics, and it's just a repeating unit of the polymer. So this unit here gets repeated over and over and over again, and it adds to each side because it's dual functional groups. Acid chlorides and acid anhydrides. Okay, acid chlorides are derivatives of carboxylic acids, and they have the general formula of the carboxylic acid right here, except the OH group is now a chlorine group. So this OH has been replaced by chlorine. That's an acid chloride. So our carbonyl group and then the chlorine. Okay, they're replacing the oleic acid with oil chloride. Okay, so instead of the OIC acid, it's OYL chloride instead of oic acid. Okay, so this one here is 2 carbons. So instead of ethanoic acid, it's ethanoyl chloride. Okay, so all you're doing is replacing the ic acid, the oic acid with OYL chloride. Okay, so this is whenever you count, it's number 1, 2, 3. So this is 3 bromo because there's a bromine group attached here. Pentane, so pentanoyl chloride. 3 bromo. I said pentane, I meant propyl. There's 3 carbons. Propanoyl chloride. Okay. Okay, benzoic acid. Okay, this is a number 1, 2, 3, 4. So this is 4-chloral benzoyl chloride, or parachloral benzoyl chloride. So 4-chloral benzoyl chloride, or this is para. Remember the ortho, meta, and para positions. And you can only use that with a benzene ring. So parachloral benzoyl chloride. Okay. Acid chlorides. Okay. They're very noxious materials. They're irritating chemicals. Require great care in handling them. They're very explosive. Okay. They're slightly polar. They boil near the corresponding Carbonell's temperature. So it's real similar to the alcohol or the carboxylic acid, their boiling point. But they do not dissolve in water because they react with water extremely violently. Okay. They react extreme violence to water, so they don't dissolve in it. They just basically explode on top of it. Okay. They're an acyl group transfer reagent. They're good for transferring acyl groups, like you're making a salicylic acid. We're transferring an acyl group onto salicylic acid, transferring a acetyl group onto it. Okay. So this is your carboxylic acid. The inorganic acid and chlorides forms your acid chloride plus other inorganic products. Okay. So you take your carboxylic acid and form your acid chloride. Okay. So carboxylic acid forms your acid chlorides. PCl3, PCl5, any of those will usually work with it. We'll get different ones here. So inorganic acid chlorides. Okay. Phosphorus trichloride, phosphorus pentachloride. Okay. SOCl2, any of those will create the acid chloride from this corresponding carboxylic acid. So if it mixes with any of these 3, you will get an acid chloride formed from a carboxylic acid. Okay. And all it is replacing this OH group with a chlorine group. And any of these 3 will catalyze that reaction, PCl3, PCl5, or SOCl2. So we went from propanoic acid to propanoyl chloride. So this is propanoic acid, and you drop the oic acid, and so you go to propanoyl chloride. Okay. Already says it, propanoic acid, and with one of those 3 reagents to propanoyl chloride. Okay, so again, ethanoic acid goes to ethanoyl chloride, presence of phosphorus trichloride. Ethanoic acid, ethanoyl chloride. Okay, benzoic acid. Okay. In the presence of SOCl2 goes to benzoyl chloride. Again, you just replace this OH group with the Cl group with chlorine. Okay, and you drop the OIC acid and you put OYL, that's a Y, chloride. All right, write equations rather than the following reactions and name the products. Butanoic acid with phosphorus trichloride. Butanoic acid is going to form with phosphorus trichloride. It's going to form the acid chloride. So butanoic acid is going to go to butan oil chloride. Okay, so here's butanoic acid in the presence of phosphorus trichloride, and all you're doing is replacing the OH group with chlorine. Okay, and you name this thing. It's 4 carbons, so butanoyl chloride. Okay, 2-bromobenzoic acid with thionyl chloride, SOCl2. So here's 2-bromo. Here's benzoic acid right here. That's benzoic acid. And the number 2 carbon is a bromo group. So 2-bromobenzoic acid. And again, what you're going to do when you have thionyl chloride or phosphorus trichloride, phosphorus pentachloride, you're going to replace this OH group with the Cl. And to name it, okay, you're going to do the same thing. It's going to be 2-bromobenzoyl chloride. You replace the OIC with OYL and add the word chloride. So 2-bromobenzoyl chloride. Okay, write equation synthesis of butanyl chloride. So how are we going to make butanyl chloride? Okay, we're going to make butanyl chloride. It's going to come from butanoic acid. So butanoic acid is 4 carbons. We'll write down here. Butanoic acid is 4 carbons put in the presence of phosphorus trichloride or phosphorus pentachloride, and it's going to form butanoyl chloride. Again, all you're doing is replacing that OH with the Cl. You drop the OIC acid, add OYL chloride. Okay, this is hexanyl chloride. So you start with hexanoic acid, 6 carbons. Replace the OH with chlorine by adding PCl3, phosphorus trichloride. Okay. What's the IUPAC name for this thing? Again, our carbonyl carbon is always number 1, 2, 3, 4. So we have a chloride here. This is a acid chloride functional group. We have 4 carbons, so it's butan oil, OYL chloride. And we got a bromine group at number 3. So 3-bromo butanoyl chloride. 3-bromo butanoyl chloride. Again, butanoyl chloride means 4 carbons with a carbonyl carbon and a chlorine. And at the number 3 carbon is a bromine group attached. Okay, OH group attached. And there's 1, 2, 3, 4, 5 carbons. So at the number 3 carbon, there's a hydroxy. Because again, we named the most oxidized functional group. So 3 hydroxy, and there's 5 carbons, so pentanoyl chloride. 3 hydroxy, or hydroxyl. 3 hydroxyl pentanoyl chloride. And again, here's your functional group, your acid chloride, 1, 2, 3, 4, 5, 6, 7. So 7 carbons. And numbers 2 and number 6, you have attachments. So number 6, there's a 6-chloral, 2 hydroxyl, hep, because it's 7 carbons, heptanoyl chloride. So 6-chloral, again, alphabetical order, 6-chloral, 2 hydroxyl, heptanoyl, and it's a chloride instead of the OH group for the carboxylic acid. One, 2, 3. So 2 hydroxyl, propanoyl chloride. You drop the OIC acid and add OYL chloride. So 2-hydroxyl propanoyl chloride. Okay. Write equations on the synthesis of the fine acid chloride and the acid chloride product. Okay. So how do we make this acid chloride? Co-reactive with PCl3, PCl5, SOCl2. Any of those will work. And we're going to start with, remember, we're going to start with a corresponding carboxylic acid because we replace the OH group with that Cl group. So we're going to start with CH3, CH, CH3, C double bond O, OH. So we just started with the only difference between the acid chloride and the carboxylic acid is you replace this OH group with this chlorine. That's it. You can name it differently. So to name that the reactant, we have 2-methyl propanoic acid. We drop the OIC acid and replace it with OYL chloride. When we switch out the OH group for chlorine group, and we have PCl3 in there. Okay. So here's a reaction. This is you draw the exact same structure, except instead of chlorine, you put OH. That's the only difference. Okay. So this is the starting carboxylic acid, which we said was 2-methyl propanoic acid. 2-methyl propanoic acid. Okay. To name the chloride, okay, we drop the OIC acid and add OYL chloride. So we get 2-methyl propanoyl chloride. Okay. Synthesis of the acid chloride. Whoops, what did I hit here? How did I do this? We got something on my screen, it's not on your screen. Okay, there we go. My screen is just acting up. All right, so we want to make this acid chloride. Again, so we just mimic this whole thing. And what's the only thing we're going to replace in this compound? We're going to switch the Cl with OH. That's it. That's all we're going to do. So this is what we start with. So instead of the Cl, we have OH. And then we have the Cl here, and PCl3, PCl5, SOCl2, any of those will work as your catalyst in the reaction. Okay, so we name the reactant, which is 1, 2, 3, 4, 5, 6 carbons. So hexanoic acid. Okay, and remember, we drop the OIC acid and add OYL chloride to name that one. So it becomes hexanoyl chloride. That's it. Just remember with acid chlorides, all we're doing is replacing the OH group here with a Cl group here. That's it. It's the only difference. Okay, so how do we make this compound? What would be the starting acid? It'd be the exact same thing, but instead of writing Cl, you'd write what? Instead of writing Cl here, what would you write?
OH.
OH, perfect. That's it. That's the only difference. A lot of students get really confused with these acid chlorides. And the only difference is there's a Cl instead of an OH. That's it. If there's no trick questions, so it's just putting OH in there. So you write the exact same thing. And instead of Cl, you put OH. And that's your starting carboxylic acid. Okay. And then you have to put in PCl3, PCl5, or SOCl2. Any of those would work as a catalyst to get that reaction going. And let's name this thing. This is 2 carbons. It's a carboxylic acid, so ethanoic acid. We drop the oic acid and put OYL chloride, so we get ethanoyl chloride. Okay, should be making sense by now. Let's do another one here. Again, you're going to write this exact same structure. So you're going to take this and you're going to write this exact same thing down again. And you're going to replace that with OH. And that's your starting carboxylic acid for your acid chloride. So you write the same thing out of it. And instead of writing Cl here, we put OH, PCl3, and there's our chloride. So to name this thing, we've got 1, 2, 3, 4, 5, 6 carbons. So we have 4 bromo hexanoic acid. 4 bromo hexanoic acid. So again, to name the chloride, acid chloride, we drop the OIC acid and put oil chloride. So we got 4 bromo hexane oil chloride. Okay. And I think there's one more here. This should do it. All right. So again, this is, well, we want to synthesize it from the carboxylic acid. Okay. So again, we're just going to take the same thing here and we're going to switch. Instead of writing Cl, we're going to write OH. So right here, we're going to write OH instead of Cl. Okay. And then PCl3, PCl5, SOCl2, any of those will work. And then this is our acid chloride. So we name our acid, we name our carboxylic acid. There's 1 carbon. So methanoic acid. We drop the OIC acid and add oil chloride for the acid chloride. So we got methanoyl chloride. There's a lot of examples of this one. Again, we're just going to switch this out with OH. So we get this one right here. We get the OH instead of the Cl. So we get propane. There's 3 carbons. Propanoic acid. And then this would be, what would this be? Someone want to guess?
Propanoyl chloride.
You got it. Perfect. Exactly right. Propanoyl chloride. You drop the OIC acid, add oil chloride. Holy cow, there's a lot of examples on this one. All right, we're going to duplicate this section right here and then substitute that for OH. That's exactly what we did. Exact same thing here, and then put our OH group on it. So this is 1, 2, 3, 4 carbons. At number 2 carbon, there is a methyl group. So 2-methyl butanoic acid, because of carboxylic acid. Okay, and we did the exact same thing. We're going to substitute. We're just going to change the oic acid into oil chloride when there's a Cl and 7 OH. So 2-methyl butane oil chloride. Okay, same exact thing. Okay, do not make this harder than it is with acid chlorides. We're giving a lot of examples here. No one should miss this on the midterm. All right, again, we're going to duplicate the same thing. We're going to replace the Cl with OH to determine its precursor carboxylic acid. PCl3, OH is now there instead of Cl. So this is how many carbons? 5, 6, 7 carbons. So 7 carbons and it's hepta. So heptanoic acid. Okay, we drop the OIC and put OYL chloride. Okay, so heptanoyl chloride. All right, hydrolysis of acid chlorides now. We're going to add water to that. Acid chlorides react violently with water in a hydrolysis reaction. Okay, reform the organic acid with and HCl. So substitution of the OH for the chlorine occurs at the carbonyl carbon. That's where it was occurring. Remember the carbonyl carbon? Substitution with the OH group was occurring right there. It wasn't occurring at the other carbons. It was at the carbonyl carbon. Okay, so when you add water to this is an acid chloride. Water attacks it right here. And this chlorine is now kicked off. And the chlorine bonds with the H. And this OH attaches to that carbon now. And it regenerates the carboxylic acid. So our chlorine is doing the reverse reaction now. Okay, instead of taking one away, we're adding water to it, and it's taking the chlorine place with OH. So it's just doing the reverse reaction now. Okay. So acid chlorides react with alcohols to form esters and hydrochloric acid. Okay, and it occurs at the chlorine that's being substituted at the carbonyl chlorine. So if we have, instead of water now we have an alcohol. Same principle. This was just an H when it was water. So this H kicks off that chlorine to form HCl, hydrochloric acid. So the OCH3 attaches to the carbonyl carbon, and you get an ester being formed. Okay. So the same thing we did with water, except now we got an R group attached. So if this was water, that would be an H, we'd have a carboxylic acid. If this is an alcohol, now we got an R group, and we have an ester being formed. The same reaction, same attacking everything else. It just puts our OH or OR back in place of the Cl, the acid from the acid chloride. Okay. Acid anhydrides. These are acid anhydrides. We have an oxygen in between two carbonyl groups. Those are called acid anhydrides. Okay. Acid anhydrides have this above formula. There's an R group at each end, and there's two carbonyl groups. And instead of an OH or an OR, now we got another carbonyl group. Okay. That's a special group called acid anhydrides. So two carboxylic acid molecules joined together with a water molecule removed. That's what calls an acid anhydride. Because we have a carboxylic acid, this is R1, COOH, and we have R2, C-O-O-H, right? And we're going to remove water from between those two. So one's going to remove OH, one's going to remove H, and this oxygen is going to bind to that carbon. That's how they're formed. So we're removing water. One gets an OH removed, one gets an H removed, and they combine. These R groups do not have to be the same. They can be different carboxylic acids that react. So when two carboxylic acids join together, it forms an acid anhydride. Remember, carboxylic acid and an alcohol, okay, form an ester. Carboxylic acid and carboxylic acid form an acid anhydride. Okay, anhydride means without water. Anhydride, no hydration. So you're taking water away from the carboxylic acid. Okay, so this reaction here would be plus water because you're taking an OH from one and H from another, and now you join two carboxylic acids together. Okay, so remember, when a carboxylic acid and alcohol, you get an ester. Two carboxylic acids join together, you get an acid anhydride. It removes the water from between them. Okay, if they're symmetrical anhydrides, it means they're symmetrical. It means they're the same on both ends. It means the R groups, the acyl groups, are the same. Okay, symmetrical anhydrides are named by replacing the acid ending with anhydride. Okay, so all you do is call it anhydride. So this would be, you have two carbons at the end of each one. So you would get ethanoic anhydride, because this is ethanoic acid, right? If this was an OH, that would be ethanoic acid. So now you have two symmetrical groups, both sides. So it's ethanoic, same thing. So instead of putting acid for carboxylic acid, you write anhydride. But that's for symmetrical ones. Okay. This would be what? What's the carboxylic acid that's formed here? If we put our H right back here, what carboxylic acid would that be?
Benzenoic acid?
Perfect. Exactly. It'd be benzoic acid. So benzoic anhydride. That's it. You just replace the acid with anhydride. Unsymmetrical anhydrides that have two different R groups. Okay. They're named by arranging the names of the two parent carboxylic acids and following with the word anhydride. In other words, so the name of the carboxylic acid may be arranged by size or alphabetically. Okay, I usually do it by size, but either way you do it is fine. I'm not going to mark it wrong for that. But this is ethanoic and this is propanoic. So ethanoic, propanoic, anhydride. So if they're the same, symmetrical, you only use the one term because it's going to be the same. If they're different R groups, you just name each R group. One was ethanoic acid, one was propanoic acid, and you replace acid with anhydride. So ethanoic, propanoic, anhydride. Okay, here's the sign. This is an anhydride, oxygen between two carbonyl groups. That's an anhydride. This is an ethyl group. This is a 1, 2, 3, 4, 5 pentyl group. So the name would be ethanoic, pentanoic, anhydride. Okay. This one, right, okay. This one has, okay, is this one, first of all, is this symmetrical or asymmetrical?
Symmetrical.
Symmetrical.
Exactly. Very good. It's symmetrical. Has the same things on both sides of the oxygen. So you have to name one. So this is 1, 2, 3, 4 carbons. So it's butane. So butanoic, instead of acid, we say anhydride. So butanoic anhydride. If there's only one term here, we know it's symmetrical. If there's two terms, then there's two different R groups. So butanoic anhydride. Is this one symmetrical?
No.
No, it's not symmetrical. I mean, this side and this side are completely different. So I gotta name the two sides. So the smaller side is 2 carbons, so that's ethanoic. Okay, 2 carbons, and this is 4, 5, 6 carbons. 6 carbons is hexanoic. So ethanoic, hexanoic, anhydride. That's how we name them. Okay, again, is this symmetrical? No, they're not symmetrical on both sides. So we named this one here. This is 1, 2, 3. The left side has 4 carbons. So butanoic, okay, that'd be butanoic acid. And the right side would be 4, 6 carbons, so hexanoic acid. So name the anhydride, it would be butanoic. We dropped the term acid. So we have butanoic, hexanoic, anhydride. Butanoic, hexanoic, anhydride. Like that, you can put it alphabetical order or you can put it by size. I usually do size, but either way is fine. All right. And is that symmetrical? Symmetrically, the exact same thing on both sides of the oxygen center. That's not,
No,
right?
not symmetrical.
Perfect, it's not symmetrical. So I name both of them. So there's 2 carbons over here. So 2 carbons is ethanoic. And 1, 2, 3, 4, 5 carbons over here. So it's pentanoic. Now, could you write, would it be correct to put pentanoic, ethanoic, anhydride?
No, doesn't it have to be alphabetized?
Perfect, you're exactly right. Has to be alphabetized or by size. So you can either put it alphabetically or in order of size. I usually start from the smallest one to the largest one. Okay, so you put ethanoic, pentanoic by size or by alphabet is the same thing. So you put ethanoic, pentanoic, anhydride. Okay, and this one, we have got, it's not symmetrical. So you got 3 carbons on this side, and we got 1, 2, 3, 4, 5 carbons on this side. So 3 carbons is propane, so propanoic, and then pentanoic anhydride. Propanoic is your 3 carbons, pentanoic is your 5 carbons, and then anhydride is this structure here with the R groups attached with an oxygen in between it. Remember, it's a dehydration reaction between 2 carboxylic acids. You've lost water. Anhydride literally means without water, no hydration. So without water, you put 2 carboxylic acids together, you've lost water, you lost OH from one, H from the other, and this is your anhydride that forms. And this is propanoic, 3 carbons, pentanoic, 5 carbons, anhydride. You drop the word acid. Okay. So 3 carbons here, 2 carbons here. So ethanoic, propanoic, anhydride. Formation of acid anhydrides, which you talked about. They're not typically formed. They're usually formed by the reactions between an acid chloride and a carboxylate anion. That's what usually forms them. Okay, so here's your acid chloride. Okay, and here's your anion, your carboxylate anion. Okay, when they form, the oxygen, okay, comes up here, kicks the chlorine off. It's your chlorine solution, and that oxygen attaches to that group there. Okay, so it's the same principle we've been doing, except the OH group now it's kicking off this chlorine and it's kicking it into solution. And the bond is being replaced by the oxygen here of the anion. Okay, it forms the exact same product that normally would. And if you name this, how would you name this product? Who wants to take a guess at it? No guesses? It would be ethanoic anhydride. Symmetrical on both sides. 2 carbon. So ethanoic, drop the word acid, put anhydride. Okay. So our carboxylic acid goes to our acid chloride. Okay. The acid chloride reacts with the anion of this carboxylic acid, and it produces the anhydride, which is a fusing of these 2 carboxylic acid groups, 1H and OH. Okay, so CH3, CH3 carbonyl group. Again, ethanoic anhydride. This is just the mechanism of how it works. It forms the acid chloride first, then it reacts with the anion to form the anhydride. Okay, write an equation for propanoic anhydride, starting with the acid chloride. So propanoic chloride.
On that,
Yes.
how come you don't, like, do you just not mention the chloride on the bottom?
No, right here.
Right. Oh, okay.
It kicks off of here. Remember that it pulls one from the SOCl2 right here.
Right. So you don't, but when you're naming, you don't mention it.
Mention.
Because you
I'm
said
sorry.
that the ethanoic,
Okay, this is ethanoic acid, right? This one
Right.
here. Okay, this one here is ethanoyl chloride.
mhm.
Okay, this one here is the carboxyl of the ethanoic acid with a basic solution.
Mhm.
Okay, and this one here is ethanoic anhydride. Plus your chlorine gets kicked off in solution.
Okay, so that's what I'm saying. The chlorine that gets kicked off, you don't mention it in the naming. I was just curious because it's all on the same side of the reaction.
You can mention like saying plus water, plus chlorine,
Okay.
plus hydrochloric acid, plus something like that. But this is just one of the byproducts. But you can mention it plus chlorine ion.
Okay, so when like we're naming the reaction, we don't have to mention that because
No.
it's been kicked off.
Right. And
Okay.
it's just an inorganic product that's being formed. It's not
Okay.
part of the organic compound.
Okay.
Does that make sense?
Yeah.
Okay, perfect. Okay. So representing the synthesis of propanoic anhydride. So we're starting with propanoyl chloride and you react it with the propanoic anion. Okay. And it forms the anhydride. Okay. Propanoic anhydride. Okay. So it's going to be 3 carbons, the chlorine, and 3 carbons with the O minus. Okay, the O minus comes and attaches here, and the chlorine kicks off in the solution, which is right here. And that's how it's synthesized. Okay, and this is propanoyl chloride. Okay, propanoate ion, and this is propanoyl. This is propanoic anhydride. Okay, synthesis of butanoic anhydride. That's our first one. So we're going to start with, okay, butanoic acid converted into the chlorine. So we start with butanoic acid converted into the butanoyl chloride. Then we have our butanoic acid here, anion, and it forms butanoyl anhydride. Okay, 4 carbons on each side. That's exactly where this came from, right here. Okay, so all you're doing is taking this chloride and kicking it off and bonding the oxygen to it here, which is the same net result as taking water away from the 2 carboxylic acids. It's just the mechanism of how it gets there. You can name it either way, but this is the process by how it occurs. Okay, butanoyl chloride and butanoate ion. And it forms butanoic anhydride. Then you want to do the same thing with hexanoic anhydride. Okay. Hexanoic anhydride is 6 carbons. So you're going to turn that into hexanoyl chloride. Okay. It's going to react with a hexanoate ion and form 6 carbons on each side of the oxygen. So it's going to be symmetrical. So here's your hexanoyl chloride, your hexanoyl ion, hexanoate ion, the negative ion, and then it forms hexanoyl anhydride. Hexanoic anhydride, sorry. It's hexanoic anhydride. Name of the acid, just drop the word acid and put anhydride. Okay, but don't get confused in just the mechanisms, because all that is just the way it does it. Doesn't change anything else. It's still an anhydride reaction. Write an equation showing the synthesis of each of the following acid anhydrides. Provide the names acid and chlorides and acid anhydride product. Okay, so how do we synthesize this? This is symmetrical, right? It's the same thing on both sides. So we're going to synthesize it from the same carboxylic acid. It's easier for me to think of it as carboxylic acid than convert it to a chloride. So you'd have this, the CH3, same product, CH3, CH2, C double bond O, and instead of OH, you have Cl. Okay. Then you write the same exact thing. I'm not real neat here. CH3, CH2, CO, and this is O minus. This one, the hydrogen's been pulled off, but it's the carboxylic acid. And the O minus connects here and kicks off the chlorine. That's the mechanism of how it works. And that's how it's formed. Okay. So again, we form the carboxylic acid, and instead of writing OH, we put the Cl. But we can form that from the carboxylic acid. Carboxylic acid plus PCl3, PCl5, SOCO2, any of those will form the acid chloride. And then you have the same carboxylic acid, just where the hydrogen's missing. The hydrogen been, it's an acid, so it's protonated, it's deprotonated. The hydrogen has gone into the solution. Okay, and now the O minus can attack that carbon with the chlorine and kick the chlorine off. So you get chlorine kicked off, and you get the anhydride. So name the first compound. What's the first reactant? Okay, 3-methyl butanoyl chloride. Okay, 3-methyl butanoyl chloride. The other one is 3-methyl butanoate ion. 3-methyl butanoate ion, because it's lost the hydrogen. And now name the anhydride. Hydrogen is the exact same name. Okay, all you do is drop the acid and add, well, don't drop the acid, but you drop the word acid and add anhydride. So this group here, this is 3-methyl butanoic anhydride. Okay, it's the same on both sides. Okay, again, symmetrical. Same. Okay, so you're going to start with, just write the exact same thing down like you would, just like we did before, H, C, double bond O, O. And instead of that O, we write Cl. Okay, and it's going to react with the same compound. And instead of the Cl, you have the O. Instead of OH, you have the O minus. Okay, because it's lost its proton. It's an acid. Okay, it's donated its proton. Okay, and then the O attacks here, kicks off the chlorine, and you get plus Cl minus. So here's the reaction. Again, we put a chlorine here. We put our O minus here. If you put the OH in either of those positions, that's your acid. That's the carboxylic acid. Oh, wait, we're not symmetrical, are we? Okay, so this, you get it either way. This is the one right here, and then we copy this one to right here. They're not symmetrical this time. So we're gonna name it a little bit differently. It's the same principle, same reaction. The O minus attacks that carbon, kicks off the chloride. So you get CH3CO, and then COOCH3, COCH3. All right, so to name this compound here, this is one carbon. If that was an OH, it'd be methanoic acid. So we drop the oic acid, put oil chloride, so it's methanoyl chloride. Okay, and this is ethane. This is 2 carbons, so ethanoate ion. Okay, and this is your anhydride. So now we have to put 2 names on it because it's not symmetrical. Okay, so it has to be, one has to be methyl, the other has to be ethyl. So methanoic, ethanoic, anhydride. Because it's not symmetrical. Okay. All right, I think one more of these. So how are we going to form this? Is this symmetrical?
Yes.
Yes, perfectly symmetrical. So we just duplicate this right here. We add a chlorine to one and the OH to the other, deprotonate it. So we added the chlorine instead of the OH, and then we put the same thing with the O minus. And we know this attacks that carbon and kicks off that chlorine, okay, to produce this anhydride plus chlorine. Okay, so to name it, we would have let's name this one first here. This is the acid chloride. So it's 1, 2, 3. No, it's not 3 ethyl. Hold on. 1, 2, 3, 4, 5 carbons. So this is number 1, number 2, number 3, number 4, number 5. Okay. So this would be 3 methyl. Okay. Pentanoyl chloride. 3 methyl pentanoyl chloride. And the other one would be, this one here would be 3 methyl pentanoate ion. It's got the negative charge. 3 methyl pentanoate ion. And the anhydride would be named, okay, if you look at this, it's symmetrical. So you name this one here. This is 3 methyl, okay, pentyl. So 3 methyl pentanoic anhydride. Okay, because you name the acid, you just drop the word acid. So 3 methyl pentanoyl, 3 methyl pentanoic anhydride. 3 methyl pentanoic anhydride. That's how you would name it. Okay. And this one here. Now this one is not symmetrical. Okay. So you'd form 1 chloride. Let's say we have, so CH3, CO, and instead of OH, put Cl. And the other one is CH3, CH2, CH3, CH2, CH2, C double bond O, O minus. That's a bond right there. Okay, so we know the O minus is going to come here, attack that carbon, kick off that chlorine, and form anhydride. And that's what it does. So there's your acid chloride. This is your carboxylic acid, carboxylate salt, okay, or your anion. And this is the anhydride. And it releases chlorine into solution. So we have got, what do we got? Let's name this thing right here. 2 carbons. So it would be, if this was an OH group, it'd be ethanoic acid. We drop the oic acid and put oil chloride when there's we leave the CO. So ethanoyl chloride. Okay. Name the anion. This is going to be 1, 2, 3, 4 carbons. So it's going to be butane. So it, excuse me, it would have been butanoic acid. So now we got the anion. So it's butanoate anion or ion. Butanoate ion. Okay, so combine these. Let's name the anhydride. We got this section here. We got this section here. We got 2 carbons here. We got 4 carbons. 1, 2, 3, 4 carbons here. So let's do the small one first, which is ethane. So if that was a carboxylic acid, it'd be ethanoic acid. We drop the acid. So ethanoic, butanoic, anhydride. That's how we name the product. Okay. So acid anhydrides rarely undergo hydrolysis. The rate of hydrolysis may be increased by addition of trace of alcohol or hydroxide base in solution. So you can increase the rate of the undergo. So you can take this anhydride and hydrolyze it by adding water back to it. It's hard to do, but a lot of heat can do it in an acid environment. And all that's going to happen is you're going to add water, just like we did before. We're going to break this apart. We're going to add an H and an OH. So we add H to this side and OH to this side. Now it can add the H and OH to either side of that division, that line. Okay, so if it's not symmetrical, you'll get 2 different types of alcohols, two different types of carboxylic acids. Okay, rather than a symmetrical division. Okay, but this is symmetrical, so it doesn't matter which side of this bond we add the H and the OH to. Okay, so this is propanoic anhydride, and this goes to propanoic acid. Okay, so all it does is add water. So it breaks this bond by the oxygen, adds H to one side, OH to the other. Okay, both is going to form carboxylic acid, which in this case is propanoic acid. Okay, when they react with alcohols, they produce an ester and a carboxylic acid. Okay, because there's an acyl transfer group. In other words, if you have an alcohol and it reacts with an acid anhydride, it's the same principle we did with adding water, except now we're going to add, so we're going to add across this bond here. Okay, one group is going to be R and OH. Remember how we added for water, we added H and OH. If it's an alcohol, instead of water, one of the hydrogens is now an R group. Okay, so it ends up with the OR, which is right here, and then the OH, which is right here. So we formed a carboxylic acid on this side here, where we added the OH. This forms a carboxylic acid. And on here we formed an ester. It depends where you add the R and the OH. Okay, it's the same thing as adding water, except now one of the hydrogens is an R group. Does that make sense? So don't get confused with just because you see all these R groups floating around and where they come from. If you think about it logically, do your division point, know that an alcohol is the same as water, HOH, ROH. So instead of one of the hydrogens, now we add R, and we get an ester, and we get a carboxylic acid. Okay, so there's your alcohol. There's your acid anhydride. Okay, there's a ester, and there's a carboxylic acid. Okay. So if you add water to an acid anhydride, you get carboxylic acid. If you add an alcohol to an acid anhydride, you get a carboxylic acid plus an ester, because now this isn't an H anymore. This is an R group. Okay. So here's what the reaction, what it looks like. This is your alcohol reactant. Okay. And this is your acyl transfer group. So this is the ester that's formed. Okay. And the carboxylic acid is formed from the other reactant of it. So it depends where you split it. Okay, there's your acid anhydride. Okay, so you get R, COO. And again, you're going to get R on one side and OH on the other side. Okay, R and then OH. So you're going to get your carboxylic acid. There's your R prime, OH, and then you get your R. This is this side here, double prime, C double bond O, O, and you added your R to it. So you get a carboxylic acid and you get your ester. That's how you form it. Okay. Again, it's just one group's going to get the H or the R, depending if it's water or an alcohol. The other group gets the OH. So the group that gets the OH is going to form carboxylic acid. The group that gets the R, okay, is going to form an ester. Or if it's an H, it's going to form another carboxylic acid. That's the only difference. It's the same kind of reaction, same exact thing. So if we look at, okay, so here's our acid anhydride. This is our alcohol. So what's going to happen? Let's draw a dividing line. Okay, one side gets the H, which is going to be here, going to bond to the oxygen. Okay, and one side gets the R group, which is going to, wait, I'm confusing everybody here. Hold on a second. Da-da-da. Okay, here's our division line. Let's divide it. One side gets the OH from the alcohol, and the other one gets the CH, CH3, CH3. That's your attachment right there. Okay. So one group gets the R group, one gets the OH. The OH group is going to form a carboxylic acid right here. Okay. The other one has the oxygen bonds to that carbon. Okay. So instead of bonding the hydrogen, now you're bonding an R group to it. So you have your CH3O right here, and this is your R group attached to it. Right there. Here's your CH3, CH3H. Okay. So always find your dividing line. And if you're on this, on the left side of the dividing line, you're always going to add the OH. On the right side, where there's already an oxygen, you're going to add the R group or the hydrogen if it's water. And those are the products you're going to get every time. Okay. So if it's an alcohol with an acid anhydride, you're going to form an ester and an alcohol. Okay. If it's water reacting with an acid anhydride, you're going to form carboxylic acids because the R group is now an H. Okay. See if there's another example of it. High energy compounds. Let's do a little more, then we'll call it a night. There's a lot of information in this last chapter here. But I want to do this, and we're going to finish this up and start at 15 next week because your final, because next week's a holiday. That's Easter break. And your midterm is going to be on the day you get back, that Monday. So I want to cover as much as I can for you guys. So phosphoric acid reacts with alcohols to produce a phosphate ester or phosphoester bond. This is what ATP is formed with in the body. That's what we're getting into. So the ester can then react with a second or third acid to get phosphoric acid and hydrides. Okay, those are ADP and ATP are examples of phosphate esters. That's why we use these reactions, how they occur. We go into these reactions in great detail in the biochemistry section of this, because ATP is extremely important in the body. Because for muscles to contract, it needs two things in the human body. It needs calcium, it needs ATP. Okay, those two things have to be present. Remember, the heart's a muscle. So for the heart to contract, you have to have calcium, you have to have ATP. Okay, so this is your alcohol. This is your high phosphate energy bond here. Okay, and you're going to phosphorylate it. You're going to put the OR group attached to it, and that's what's going to form your pyrimidines, your pyrides like DNA and RNA. That's what's going to form your energy for your bases to form when you form genetic code. So again, it's the same reaction we've been talking about. This is the exact same thing right here. POH, OHO. We're taking an OH and replacing it with an R group. Okay. This can be a phosphate ester. So you're forming an ester. Okay. It's a high energy bond that helps take ADP to ATP. Okay, you have an alcohol, you got your phosphoric acid, okay, and you're forming a phosphate ester. Same thing, we have your carbonyl group, except now we have a phosphate group here instead of a carbon. Okay, we've got your oxygen, and then we got our R group. So it's a phosphate ester that forms. Okay. Let's do this slide, then we'll stop. Phosphorus is the simplest sugars or monosaccharides are important in all energy harvesting biochemical pathways that provide energy for all life function. One such pathway is glycolysis, breaking down of glucose to produce ATP. And we're going to study that in great detail. This is the first stage in the breakdown of sugars in the body. Okay, the first reaction is the formation of phosphoester of the 6-carbon sugar glucose. So we're going to form a phosphoester of the 6-carbon glucose of the 6-carbon sugar. The phosphorylation is glucose produces glucose 6-phosphate. Okay, so we took glucose, and we'll stop right here. This is glucose. We add ATP with it. It takes energy to phosphate it. We added a phosphate group to the glucose. We give it a high energy bond, which can now be used for energy in the body. Okay, so this is beta D-glucose, and this is beta D-glucose 6-phosphate. Okay, because we added a phosphate at the number 6 carbon here. This is the number 1 carbon. Okay, if the OH, where are we at? 1, 2, 3, 4, 5. Yeah. Got it. Okay, so beta D-glucose and beta D-glucose 6-phosphate. You're adding a phosphate group to the number 6 carbon. This, I messed that up. Hold on. This is the number 1 carbon here, right behind the OH group. This is your number 1 carbon. If the OH group is up, then it's going to be beta. The OH group is down, it's going to be alpha. That's where the beta come from.